Hi, welcome to week number 5, moment of a couple, reduction of a force and couple systems, and reduction of simple distributed loads. And this is a very nice week because here we find where the moments come from, right? And how simple structures will develop moments, right? So this is the set of lectures that will show us that. So for starters, right? For starters, let's talk about couples, right? Couples is the first topic we want to cover. Just a brief recap, right? Just a brief recap. Right hand rule, right? A cross B is equal to index finger A, right? Middle finger B, and the thumb gives you the sense of the arrow, right? A cross B, where the cross product vector goes, right? So right hand rule, don't hurt yourselves at home, right? Always be mindful of your vectors. Couples. A couple is a system of two parallel forces of equal magnitude, right? Two parallel forces of equal magnitude. Two parallel forces of equal magnitude. That's the key, right? For having a couple. Opposite sense, right? Opposite sense, and that's where our rotation comes from. Separated by some non-zero distance d, right? So they have to be a distance d apart, where d is measured perpendicular to the line of action of the forces. So here we have our two forces, right? One is acting up, right? And one is acting down. They are exactly identical and they are separated by a distance d, which is perpendicular to both vectors. So sometimes, right? Sometimes we just don't have a rotation, right? Just floating in space, but we have two parallel forces, right? Coming and going in opposite senses. When these forces act on a body, right? When these forces act on a body, right? This force will, or this set of forces will tend to create, right, a rotational effect that will act upon the body. So for example, I have here a beam, right? I have here a beam, and let's see if we can calculate the moment. Let's see if we can calculate the moment that these two forces create, right? And then we have a beam, right? We could have, you know what? This could be a beam. It's part of a bridge, right? So in this side, right, some ground, right? And then the river is down here, right? So, and that beam is acted by two forces, right? As shown, these two forces are 5 kilonewtons each, oriented 45 degrees from the horizontal, right? And we have a point of reference, right? B, and then this force is acting, right, on point A, right? This force is not named, right? We can call it C or whatever, right? This point we can call it C, and C and A are separated by 250 mils, right? And A is 200 mils apart from the start of the beam. So let's see if we can calculate what is the total moment caused by these two forces, right? By these two forces. So let's see, right? Let's see about the equilibrium, right? Let's see about the equilibrium that these forces will make. So remember, right, to add forces, right? To add forces, we have, or it's a good idea to break them down first. And let's start with equilibrium, and let's start with sum of forces in X, right? And then sum of forces in Y. Let's see what happens. So let's have these, right? These are the components. These are the components of force number 2, and these are the components, right? Let's see if I can use color maybe here to make it more clear. So here is force 1, the components. So we can see here that the horizontal components, right? This guy and this guy, they cancel each other out. And what about this guy and this guy? They cancel each other out. So force in X equal to 0 and force in Y equal to 0. We may feel tempted to say that this body is not going to move, it's going to remain at rest, but we haven't applied our brand new equilibrium equation, which is moments. if we have an unbalanced moment, right, we will have a rotation and this beam will go flying, right, in the air. Right, this beam would go flying in the air. So let's see how much moment these forces are causing, right? These forces are causing. So here are my forces, right? And then somebody else broke these forces down into components already, right? For example, here we have, let me see, well, they have only one force, right? Let's take moments, right? Moments about any point, right? Let's take moments about any point, and then see what sort of rotational tendency is going to appear, right? So, for example, take moments about point A, right? Where is my point A? Let's do it in green. Let's take moments about point A, right? Remember, we don't have to worry about the forces, the original forces. They were broken down, so I'm just going to cross them here, so we don't worry about them, right? And then we continue with our green color. We're going to add forces about point A. Well, these two forces, right? This force over here, right? Or this component and this component, they both have a zero moment arm because they pass both through A, so they don't count. Right? These two forces don't create moment about A. And what about this force? Well, its line of action passes through point A, so this guy is not, we don't have to consider it. So the only force alive is F1 sine of 45 degrees, right? And the distance about point A is 250 mils. 250 mils. So the moment caused by this force, right, it will be F1 sine of 45 degrees, that's a component, times 250 mils. Right, times 240 meters. This is kilonewtons and this is millimeters, so that it is 884 kilonewton millimeter. That is the moment that couple causes about point A. Okay, question for you before we go into the next slide. Okay, so we had a beam, right? We had a beam. Let's summarize what we just found, right? So we had a beam acted by two strange forces. Right? And we were told that these guys were a couple, right? And we got that the moment of these forces about point A was 884 millimeter, right? What about, right? What about we change the point in which we calculated the couple? What about we actually add forces about B? So a completely different point. Would we obtain the same moment, right? Would we obtain the same moment? Would it be the same or would it be different? That's a good question. Let's see how couples behave. So if we now consider moments about point B, right? Let's use our nice green color right here, green color here. Moments about point B. Okay, so let's get our components, right? Let's get our components. Well, these are the components that are missing, but both of the green components, they don't count because, right? Because they pass, the line of action of them pass through point A, so they don't count, right? And remember, the original force doesn't count anymore because we broke it down into components. The only forces alive are F2, 5 kilonewtons. Well, this guy is right? This guy is F2 sine of 45 degrees, right? And then this is the same thing, right? This is F1 sine of 45 degrees. And now, right, we calculate the moments of these two forces, right? This guy and this guy about point B. So let's do the first one, right? Let's do the first one. The blue force, right? The blue force times the blue moment arm. So it is F1 sine of 45 degrees, right? F1 sine of 45 degrees times the moment arm, which is 200 plus 250 mils, right? This creates about point B, this creates counterclockwise moment, so it's positive, right? Positive. But then the moment of the red force, right, will cause clockwise moment, so that's going to be negative. So that's why it has a negative sign here. So it's F2 sine of 45, sine of 45 degrees, times the moment arm, which is 200, that red moment arm is 200 mils. And that is equal to 884 kilonewton millimeter, right? So we got the same, we chose a completely different point, and we got the same moment, right? Did you notice something strange? We get the same moment regardless of where we calculate the moments. Now, this is no coincidence, right? This is no coincidence. This is no coincidence. And if we actually go back to the definition of a couple, right? Or if we, right? If we remember that moment is equal to force times distance, right? To force times distance. And then we chose just, I mean, the line of action, right? The line of action of these two forces. We know that that force is sliding on this force, and it doesn't matter. And then we have, right, this force over here. And we choose a point here on this force, right? This force creates no moment with respect to this point because the moment arm is 0. But this force over here, right, it does create moment. And then based on geometry, we can calculate that this moment arm is equal to 250 sine of 45 degrees, right? And in this case, if we apply the definition, force equal to times the distance, right? The force is 5 kilonewtons times this distance, right? 250, right? 250 sine of 45. Let me see if I have the calculation. Yeah. So 5 kilonewtons times 250 sine of 45 degrees, we get the same value as before. So we can check equilibrium at different points in the body, or we can just simply choose one of the forces times the distance to the other force, as long as that distance is perpendicular, and that will get you your moment, right? The moment that you need, right? And it will give you exactly the same moment. So summarizing, right? So you have a couple, right? So the moment can be obtained by adding equilibrium at any point of the rigid body, or just choose one point and then multiply times the distance to the other force, right? And then that will get you the value of the moment you seek, and it's the same, right? And what we have is the general case, right? So what happens if we have these couple vectors in 3D space? Let's see how we can calculate the moment. And let's start very easy, right? So we have two vectors, right? Just floating in space. Floating in space, they are identical in magnitude, they are opposite in sense, parallel. And let's use what we know about moments to calculate the total moment of these two vector forces, or force vectors about point O, right, in this case. The total moment is equal to the sum, right, the sum of the cross products, right, that position vectors shooting from point O to the vectors, right, will have. So we shoot the first position vector, right, let's call it RV, right, to the first vector F, right. Let's see if we have it here on the equation. Yeah, we have it. So this guy will be RB cross F, and then we have a second position vector, RA, shooting from point O to point A in vector minus F. And then the cross product, right, the moment caused by that force will be equal to RA cross minus F. And then all we have to do is to add these two cross products to get the total moment. So once we do that, we add RV cross F plus, right, RA cross minus F, and this is equal to RV minus RA, that is associative property, right, cross F, right. And then let's take a look at the situation of these two vectors, right, because this is going to be really important and it's going to make our lives very, very easy. Take a look, right? Take a look. We are happy with this result, right? We have to be happy with this result. But we are looking for something simpler, right? Something simpler. Now that something simpler is here, right? Here in the bottom, and here in the bottom. But let's take a look, right? So we have RV and RA. Well, what about I give you RV minus RA? Right? Just wait with me, right? Hold with me. Give me a little bit of your time, right? Just to entertain this concept. So, if I subtract, right, or I do the subtraction, it should be RV minus RA, right? So if I do RV minus RA, just humor me a moment. Let's subtract RA from RV. Okay, so we can do simple. Addition of moments, right? So if I add RV plus RA, I have to put tip to tail, and this is RA. So this guy, this vector over here is RA, or let me just put it this way. This guy is RB plus RA, right? This vector here. Now, to subtract, I just have to add the negative, right? The negative. So the negative of RA is this. And then I can do tail to tip, right? Tail to tip. I can do this one. And this is RV minus RA. Guess what, right? This vector over here, RV minus RA, is equal to this vector over here, right? Vector R, right? And then hold on to that thought. What if, right? What if, and this is something really magical. What if I have two vectors, right? Two vectors floating in space. Two vectors floating in space. What if I could calculate the moment that these two forces have, right? About point O or about any other point, right? Because we saw that couples generate the same moment everywhere. What if I just could shoot a position vector from one vector to the other? It doesn't matter that it's perpendicular to both or whatever, right? If we know this point in this vector and we know this point in this vector, we just shoot a position vector between the two, and that should give me the moment. Well, since RV minus RA is equal to this vector R, right? Since this RV minus RA, I'm here, is equal to a vector R, right? I can do just that, right? I can calculate the moment that vectors in space have, right? By just shooting a position vector R from one point in one vector to one point in the other vector. And then I do just, for example, if I decide to do it, I have to use this force vector. So I can do the moment or the couple moment, right? Couple moment equal to R cross F, right? I'm using this position vector and I'm using this force vector to calculate my couple moment, right? And I don't have to even go to the origin or to any other point, right? So that's something really magical that we can do with couples in space, right? Just a shortcut, and then something really direct, and we use the advantages of the cross product, right? So this is just further proof, right? Further proof that we don't really have to go through the origin, right? It means that a couple moment, right, depends on the vector R between the two forces and not on point O or any other point, right? Or any other point for all intents and purposes, right? So, well, that's something really magical that couples in space have, right? And it means that the moment caused by a couple, right, it's a free vector, right? where the physical effects depend on the vector itself, right? And not where the vector is located. So wherever the value of the couple is, right, it will create the same moment everywhere and always, right? That's something, again, something really, really magical about couples, right? So why, right? Why? Because, right? Because we have these two forces in opposite sides, right? So they cancel each other, right? If we add them in X, for example, these two forces will cancel each other out. So there is no translation of effects, and then there is only one definition of couple, right? One definition of couple as R cross F, right? R cross F. Careful which orientation you give to the position vector. If you want to shoot the position vector from this point to this point in the way shown, you have to use this force. If you happen to define your position vector from here to here, then you have to use this force, right? Always R cross F, right? You shoot the position vector, you hit a force vector, that's the one you have to cross. That's the one you have to cross, right? That is the one you have to cross, right? In this way. So I have an example, right? I have an example, and it's coming back to 2D, right? I have two forces, right, which appear to be identical, right? 5 kilonewtons each at 30 degrees from the vertical, right? And we are asked to determine or to find the magnitude and sense of the couple moment. They didn't even tell us where to find the moment, because it doesn't matter, right? They could have said, you know what, calculate the moment of those forces about point O, or calculate the moment of these two forces about point B or A, and it should be the same, right? It should be the same. That's why they don't even say where to calculate the moment, right? So that's something nice. One very quick answer, right, could come if we have the patience to apply trigonometry principles and actually find this distance, right? The distance perpendicular to the two vectors, right? But it require a bit of trigonometry, and will be a bit of time consuming, right? So another way would be to choose one of these 2 points. We could choose A or B, or we could choose point O to calculate the moments of these forces about. If we choose O, right, we make it a bit harder on ourselves, because these two forces, right, all the 4 forces that we have here, right, the 4 components, they have moment arms with the origin, right? But if we choose point B as suggested, we can eliminate this force and this force. This is already broken, right? Broken down, so we don't have to account for it, because those forces have no moment arm, and we just have to worry about AX and AY, right? So if we do it that way, right? We find that. Let me see if I have the notation here. No, so it appears to be here. So let me show you what happens, right? Let's use red color. So moments about B, right? Sum of moments about B. AX, this is numerically, and AY, this is numerically, right? Going left, going down. So somebody else calculate the components there. The moment caused by X about point B, right? This is the line of action. So it would be 3 meters apart, because this is 4 and this is 1 meter. So this is 3 meters. So we have AX times 3 meters. It goes about point B. It goes counterclockwise rotation, so it's positive. And then what about AY? Right? AY is 0.5 meters plus 2 meters from B. So it is 2.5 meters, right? And it creates about point B counterclockwise rotation, so it's also positive, right? And once we do the numbers on this, I have AX, I have AY, I have the moment arms now. I find that the moment is equal to 18.3 kilonewtons per meter, right? So that's one way to calculate couple moment, right? It doesn't matter where you take the moment. Choose a point that makes it easy on yourselves, right? Or if you are brave and if you have these forces, right? If you have the patience, just try to find the perpendicular distance and then multiply times F times the distance, and then watch out, right? Because in this case, right, this moment makes this rotation, right? Provide that rotation as your answer, right? So it's a simpler process, right? Or it could be a simpler, depending on you where you choose your point, right? Where you choose your point. So what about you calculate moments about A? You should obtain the same result. And since we are talking about this, why don't we calculate moments about point O? We should obtain the same result. Why don't we find this perpendicular distance and we do force times distance? We should obtain the same result, right? That is something nice about couples. And the time has come in which we have a three-dimensional case. You were waiting for this, right? So remember what we discussed, right? We don't have to calculate the moments of these two forces about the origin or about any point in the 3D plane, right? We can just shoot a position vector from force vector to force vector and then cross it with the vector you shot, right? For example, I have here two forces. They seem to be identical, but in opposite sense. And you see that all the components have different signs in each other's on the mirror image of the vector, right? So opposite vectors equal in magnitude, and we can shoot a position vector. Let's try to shoot, right? The moment will be r cross f. Let's define our position vector based on the force you want to use. So what force do you want to cross with r? Plus f or minus f? It doesn't matter, right? So it's wherever you want it to be. Let's assume you want to use plus f, right? So this you want to cross with that force vector, which means that you have to define your position vector from A to B, right? You have to define your position vector from A to B, so you can use the force vector over there, right? So position vector A to B is the coordinates of B, which are here, minus the coordinates of A, right? And we obtain a position vector A to B, right? So let's skip. So this is the position vector A to B, which we can cross with vector F. So we do that with a cross product. Remember, we are crossing with that vector because the position vector is from A to B, so we have to use this force over here, right? We use the force that we shot. That's the one we use, right? That's the one we use. So we set it up as a determinant, and we obtain that the moment, right, has this value, right? That is the couple moment, right? That is the couple moment we got. And then you could try to verify this by calculating the moment of one of the forces about the origin, calculate the moment of the other force about the origin. You add them together, you should obtain this value. So this is the end of the couple moment. We are going to discuss in the next lecture the concept of equivalent couples, right? So you have a pair of forces floating in space that cause a rotation, a certain rotation. There could be another set of forces also floating in space that could generate the same rotation, right? The same rotation. So this and more, right, we'll explore in the next video, right? So see you on the other side.